All right. Hi, everyone. I hope you recovered from the party by now. As you may be able to hear, my voice is still in recovery right now, but I think we can make it through. Yeah, first of all, super happy to see so many people interested in the topic of this talk today. So we are going to talk about predictive preloads and whether they can be something that that is a game changer for web performance, or whether they are just a gimmick that actually doesn't work in production. So before we get going, a few facts about myself. I've actually studied just a few hundred meters from here at the University of Hamburg. I did my master's degree in 2016, and I heavily focused on distributed databases, caching technologies, and also machine learning. And also during that time, I got to know the guys from SpeedKit, and I actually joined their research spin-off, also from the University of Hamburg, back in 2016. And yeah, the idea of SpeedKit is essentially to revolutionize web performance by using dynamic caching techniques and algorithms. And we've actually come quite a far way since 2016. And now we're actually powering some of the biggest e-commerce shops throughout Europe and the world. You might be able to see some of these labels below and might actually know them. They actually become pretty important during this talk because for them we are doing not only website acceleration but also monitoring of their performance. So we actually have access to data, performance data of over 200 million users per month. And that is really key when it comes to predictive pre-learning, as we will see. But first of all, let's take a look at what is actually the problem that we are trying to solve here, and what role can predictive or preloading in itself play here. So first of all, let's look at kind of the standard bottlenecks that you have in web performance. And it starts with a browser actually making a request for the page. So the first thing that the browser needs to do is load the HTML document. And as long as this is loading and the server's processing everything, the browser can't do anything and just has to wait. This is also our first bottleneck because servers tend to need some time in order to process the request and then send back the HTML to the client. Once this is then there, we get the second phase, which is loading all the dependencies of this HTML. So your JavaScript, CSS, fonts, or whatever the website needs in order to render. And here it comes down to kind of network latencies, the topology, your critical rendering path, and a lot of different optimizations. But once this is all there, then we have this third step, which is execution and rendering in the client. And this is also then our second and our third bottleneck. So we have the network and loading of dependencies, and then thirdly, the browser itself, where we try to build lean front ends that perform really well. Now, when you imagine preloading coming in here, the idea is actually to not even need to make this page request over the network anymore, because we have preloaded that earlier. So if that is the case, that gets rid of our first bottleneck. And if our preloading is really clever, we can actually also have already downloaded all the dependencies that we see in our second bottleneck. And then actually the only thing that we are left with is the browser being in a situation where he already can execute and render. So in theory, at least, preloading can get rid of 2 out of 3 major bottlenecks in web performance and could be an actual game changer. Let's see if that also translates into production a few slides later. Before we actually do that, let's first take a step back and look at what is actually predictive preloading. And I would like to start with kind of a real-world example to get you all up to speed before we dive into websites again. And the idea is here to let's imagine ourselves in a situation where there is a global pandemic. So this is kind of our current state. And now people tend to make predictions out of their current state. So what we might predict is, well, after a pandemic, potentially society breaks down, anarchy takes over, and this is then our prediction. And based on that prediction, what we think will happen next, we can actually act and do a preloading. So of course in this situation we will go to the supermarket and preload on pasta and toilet paper. So essentially super simple. We have a current state of prediction, and then we act on that prediction by preloading. Now this seems really simple, but it also shows some kind of pitfalls to this method, right? So if our prediction is not on point, then we are preparing for something that is not going to happen, and all that we preload we probably don't need. So this is, for one, our prediction always needs to be really good and on point. Then the second thing that we also need to consider is, does the system that we are working in actually support those preloads? Because if everyone goes to the supermarket and buys out all the toilet paper, there will not be any more toilet paper for people that actually need it. And so our system has kind of a limit to what can actually be preloaded. And this turns to be out also in kind of web and production to be a major bottleneck. But now let's try and make the same model also possible on the web. So what does that mean? There again, our current state is we are currently on a web page. This is a shop category page, and now we are doing our predictions on it, which means we are kind of assigning probabilities to what the next page of the user might be. And based on those probabilities, we can then decide in order to preload stuff. So essentially, really similar and simple. And again, our prediction model will be key here. And secondly, it is also super key that our system that is behind all this can handle these preloads and increased request load. So in order to actually implement a system like that in production, what do we actually need? What is kind of what are the building blocks of a system for preloading, and what do we need to consider for all of these system types? So first of all, it all starts with tracking usage data, because we need some idea of what our users on the page actually do. And the better the quality of this kind of data that we have, the better our model can actually learn and predict from that. If we have garbage data in, we get garbage predictions out. Then the second thing is we need to define and train our model. So actually, based on the data that we have, we need to find some way in order to make predictions. This can be a simple model, this can be a complex model, but it's key to have a good accuracy in that model. And then thirdly, we will have our what we will have to do is take that model and bring it into the client in order to do the preloading from there, because the browser in the end needs to be the one that does the preloading. And we need to consider what can actually our system, can this actually support preloading? And this is where we see in production a really big problem. So even if you're doing everything with the correct and best data quality user tracking, and then you're doing awesome prediction models, most often the problem, especially in kind of complex large pages like in e-commerce, comes with actually preloading stuff. And one of the major problems there is definitely server load. So we're not talking about kind of 5% more requests here when we are talking about preloading, but we are talking about like twice, 3 times, 4 times, 5 times the traffic that we have that we need to support in our applications, and that our server all of a sudden need to render. And this is, in most stacks that I know, completely unfeasible as they are standing right now. There are also a few other problems, like personalized pages in preload caches. They can get stale when they are then retrieved when the actual load happens, or even preloading stuff can change the user session in the background, like recommendations will think you visited a page even though it was just preloaded, and then things get messy. But the key problem definitely is the one of server load. And what I would infer from that is preloading is only really viable if you do caching on level of HTML. If that is not there, you probably don't need to consider preloading, at least not at the scale that we're trying to do in order to really boost performance. And right, now I don't want to tell you we can only use this for our private blog that is cached in Akamai and we can squeeze another 2 milliseconds of performance out of this. I really want this technology to be possible on large scale web systems. And in order to do that, I will now show you on one slide what SpeedKit actually does and how SpeedKit can enable complex websites to cache their HTML and to enable preloading to happen on them. And the idea is actually pretty cool and unique, I think. So SpeedKit is kind of fancy caching technology works like this. It is not implemented in your backend or infrastructure stack. As a matter of fact, you can leave that completely unmodified. Instead, SpeedKit is implemented in or activated in the browser, and it kind of changes how the website is loaded from the browser side. And the way that it does this is via service workers. So essentially, it will spin up a service worker for all the end clients. Service worker is essentially a network proxy in the client, so it will see all the requests that the page does. And let me show you how the loading of the page now changes with SpeedKit. So instead of doing this one HTML request, with SpeedKit, the service worker will actually do two, and those will be in parallel. One of them will be to a caching network, a caching hierarchy, that actually loads the anonymous version of the page. So no user session data attached to it whatsoever. You actually just get the public version of the page that the Google bot would see, for example. And the second request, it will have all the session data attached, all the cookies, and it will go to the original server backend. And now, obviously, the cached version will come in much faster. It can even be cached in the end user's device itself. And then the browser can start doing stuff. So, for example, loading all the dependencies and even start rendering this anonymous version of the page. Now, it will definitely miss a few things that are only in the personalized version. So, for example, a sales banner up here or a personalized price on the right. And once the same HTML file, but with all the personalized bits from the server comes in, which takes a bit longer, then these two documents are merged together in the client and all the personalized bits appear. Now, I could talk for like 3 or 5 hours about how that actually works and how it's possible and how it's super robust, but we're here for preloads, so just the main takeaway here is what this enables is actually for us to do preloads on those systems, because we can now do the preload on this stage. So we are preloading the cached version, the anonymous one that is served straight from the cache, which can sustain immense load. And we don't do the personalized bit yet. We're only doing this once the user clicks, and then have actually fresh data that doesn't corrupt the backend and doesn't cause a load problem. So that for the whole idea. And next, I would like to focus the remainder of this talk on how do we actually train models, or what models actually would apply, and where do we go from here, and also show you how this actually behaves in production, at least in the first forms. In order to do that, we first need to talk about success criteria, because after all, we're kind of trying to reach a goal here, and we need a way to compare different models to each other. So our essential success metric in the end will be we want to improve user perceived performance. And that means the only way of testing that really is we need to do an A/B test in production with an actual real workload. Then we do 50% of users with preloads, 50% without. Then we need to capture all the user perceived performance metrics, like, for example, largest contentful paint from the Google Core Web Vitals, and then can, in the end, compare both groups, which actually performs better than the other. This is super important to do. If you don't do this in the end, your prediction can be super good, but if it doesn't lead to user perceived performance gains in the end, it's essentially worthless. So you really need to do this in the end. But this is definitely not a good model in order to train and test different models against each other, because you are not only going to do A/B tests for the next 10 years. So instead, what we will do is look for essential machine learning models and how they actually measure the success or the quality of those systems. And that is with recall and precision. So if we want to have a well-working preload system, we need to calculate what's the recall. So all the we have all the navigations that could have been preloaded, and we use this as a divisor for all the preloads that we actually achieved. So how many of the pages did we actually preload? And the second metric is the precision, which is all the preloads that actually worked divided by all the preloads that we had to do for this. And you can optimize those individually super easy. You can just preload everything and have perfect recall, or you can preload nothing and have perfect precision, but we want to have kind of a balance of both. So we will look for the F1 score, which is the harmonic mean kind of standard metric that combines both of these. But now, with that said, let's go and talk or look at the first model that could be used for preloading just as a baseline, because this one is actually pretty simple. It doesn't use data at all. It's just implemented in the client, and it's called hover preloads. You probably might have even heard of it. There's also Guest.js, an implementation that uses kind of parts of this for Google Analytics and static site builders. But the idea here is when a user hovers over a link or touches on a mobile device, then we preload. That I would expect that to have quite a good recall, because it's hard to navigate somewhere without hovering over the link, but not, of course not 100%. So let's look at some actual data. So we measured that, we tracked what was hovered and what was touched and all the sessions for some of our customers, and this is the data based off 1 day where we evaluated this, and we will use the same day for all the other models to keep things comparable and consistent. So what we can actually see here is for that 1 day we saw 150,000 navigations. From those we preloaded 109,000, which is quite good, and we did 1.9 million preloads in order to do so. That is a lot. So we actually have pretty good recall, 71%, at least in this domain. Not maybe for your ML trained decision model of some images, but for this is actually super good. We have a precision that is pretty mediocre with not even 6%. So our F1 score is 10.73 in this case. But this great recall comes with some limitations. And those are hovering as kind of a trigger of when do I preload in the process of the user being on the site is super late. So you have a good chance of the user actually clicking on the link, on mobile even more, and the browser then loading the page before you have actually preloaded the page. Then you have to do in the service worker collapsing of requests, but still you don't get the full benefit of your preloads when you're doing them that late. So take this great recall with a grain of salt if we are looking at other models right now, just for comparison's sake. Then also the precision is not really cool, and the model completely ignores JavaScript navigations, because if there is no link to hover over, it obviously can't preload anything. So with that said, let's look at actual models that use our data and not only kind of the information that the user gives us ad hoc on the page. And one of the methods that really screams at us, use me for kind of link transition probability stuff, is Markov chains. Maybe you have heard about that already, maybe it's some years ago, so let me do a quick recap. Markov chains are essentially stochastic models, and they model essentially state machines and the transition probability between states. The classical explanation or the classical example is always with these weather states, and we have sunny, cloudy, and rainy. And the Markov model now, it models the probability from going at 1 day of sun to the next day of clouds to the next day of rain and so on. And the one property that all Markov systems share is called the Markov property, and that is super important to make our modeling and our work here much easier. And this is stating that the probability to go to the next state, it only depends on the current state. So when we, for example, see it's cloudy today, the probability that it will be rainy tomorrow only depends on today. It doesn't depend on the weather of yesterday at all. Yeah, that's also in the formula, so it actually kind of shows that you can kind of remove the whole history of that. And the cool thing about this is you can then have your probabilities in a matrix, because you have kind of all the state transitions are the matrix rows, and then the columns are the next states. So you have the probability. If it's sunny today, 50% chance it's sunny tomorrow, 30% chance it's cloudy tomorrow, and 20% chance it is rainy tomorrow. And we can apply exactly the same method to URLs. So we obviously get way larger matrices, because we have a lot of unique URLs, and we get also really sparse matrices which have a lot of zeros in them, because you can't go from every URL to every other URL, obviously. But that actually, that kind of works. It's a bit debatable if the history actually doesn't have an impact on the probability of the next step, but you can kind of a little bit argue that we can at least try that model and see what its metrics put out. So let's do that. Let's apply Markov chains for link preloading. So our algorithm is super simple. We are using the session data that we've collected with real user monitoring, and we compute the transition probability matrix out of this. And then once we have this matrix, which is pretty large matrix, then on every step that we are on, we will be looking we'll be looking into the row that corresponds to that URL, and then we get a vector out of it that has all the probabilities of the next URL for us. And now when we have that, we need a decision criteria to, based on that probability vector, decide which URLs do we preload. Do we preload the top k, so the top 2, for example, with the best probability? Or do we define a threshold of probability, like 2%, and then we do preload? We've actually tested this or evaluated this on top of our data as well. So we have now 1 week of training data, 2 million sessions, 9 million transitions, a really big matrix that I had to kind of make a bit smaller because it was running for days and I wouldn't finish. And then we have testing data. That is this 1 day that we talked about. And this is not included in our training data. This is super important. Don't kind of use the same data for testing and training. And this is kind of 1 day, 276,000 sessions. And what we can see is when we use our top K, we are getting to these kinds of results. So anywhere between a recall of 16 and 33% there. So recall is going up when we go up with the K, because we're doing more preloads. But obviously precision, or maybe not obviously, but precision is going down. And then we see the F1 scores, which are kind of close to what we saw with the hover preloading. And we can also do this with the T thresholds, and we get even better results this time. And you can really play with those thresholds quite a lot. You can also do vectors of multiple thresholds if that is your jam. And we get actually pretty good F1 scores compared to even the hover preloading out of this really simple method. Now, this has a lot of limitations still. One of them is we don't consider the history of URLs in our sessions. We only look at the last state and then the next. We also just need, or we only use a fixed amount of time for training and don't do any weighing. And then we also only used URL data. We didn't use any other features of the users or of the pages that we see in our real user monitoring, which is obviously just kind of one data point out of really many features. And then we are not considering any information on the page itself, so whether the link is even visible and could be clicked. It's not important in this model. And we are also not considering new URLs. So when the Markov chain doesn't include a URL, then you can't predict anything. So there are two methods in order. There are two really cool and fancy ideas of how we can solve the first two limitations and still apply Markov chains. Let me quickly go over them. We don't have too much time because I'm talking not fast enough. So one of them is, now we want to add history. And the idea here is, so Markov chains, they don't have any history. And if we would consider the full history, and then the complete probability space would explode and we couldn't compute anything. But there is a cool trick that we can do. So currently we're only considering the last URL and one-step probability with our probability matrix. Now if we go to multi-step probabilities by doing the cube of our probability matrix, we can actually say, okay, what is the probability to come from 2 steps from this URL to this URL? And this we get just by cubing the probability matrix. And we can do this for kind of the whole session, then you get a complex formula like that. And we are doing weights to them. So we are weighing the last state the best and the other states kind of a little bit less. The other idea is to also add more information in form of the time, because what we have seen during kind of training these models is if you choose a too large time frame, like a month instead of a week, you get worse performance in your models, because you're learning things on a website that is constantly changing that are just not true anymore. Maybe these products don't exist, maybe these URLs have changed, and you're still learning this from old data. So newer data in most situations actually is better for the algorithm. So what we are trying to do here is to use recent data more than old data. And the way that we do this is we compute one matrix actually for every day that we have, and then we add these matrices up, but do some exponential smoothing. So actually have a exponentially decreasing weight that we multiply with it. So yeah, you essentially get a matrix that has this time component also in it. We've again tested this same data training and test set as before to have this comparable. These are the threshold, and we actually see an increase in the performance of our predictions, but not by much. So going fancy is cool, but not always kind of the best step that you can do. So still we have a lot of limitations, and I think from here we are not here to do kind of more fancy stuff to Markov chains, but we actually should consider what is the data that we're actually using. So far we have only used URL data, and already we are coming to numbers that actually are meaningful when we consider them for preloads. If we now use actual features to separate kind of the probability space a bit more, this can become super powerful in that you get much better models. So you can consider different devices to be actually different when it comes to clicking links. Browsers, first time or returning users behave probably differently. Logged in users, different page types perform probably differently. Different traffic sources, or even the position and size of links. You could definitely implement those kind of Markov chains for every combinations of these attributes and dimensions, but you would end up with a lot of different Markov models, and you would need a lot of data for that. So the big question for me was, is actually mathematical modeling, as we heard in the talk yesterday, the right tool here, or should we consider something actually more fancy like machine learning? And I think we actually should, because the problem and the limit to these mathematical models is when you're doing them for a lot of different dimensions and training them for Safari mobile users that are logged in with on product pages, then you get a lot less data that you can train or that you can extract your probabilities from, and these probabilities get kind of meaningless. Also, you can't learn anything for new URLs that you've never seen, or for new dimensions that you've never seen, because it's just a mathematical model where you put in your input vector and then get hopefully some probability out. And learning algorithms in those cases where you have a lot of data and a lot of different dimensions where you're not sure which of those are actually the most meaningful in order to solve a problem, then machine learning, and especially deep learning, comes in and actually can be of great benefit. Because then you can kind of learn dependencies between your dimensions and what URLs should actually be preloaded. And we are currently actively working on this and searching for models that work better than the probability-based approaches right now. I don't have too much data on that yet, but it's a super interesting topic, and I see great potential in that. And this is kind of one of the new features that we're currently working on. But as I promised you in the beginning, we don't only want to look at recall and precision and F1 scores and kind of theory of how good is our prediction. What we care about is, does the page actually load faster for the user? And in order to validate that, what we did is, again, this production A/B test where we had 50% of users using the preloads and the other 50% not, and then compared the performance in the end. We did this for a few 100 million users on different pages, and we used a really basic preloading setup. So no machine learning, no fancy, not the full-blown Markov chains in different dimensions, but kind of harbor preloads with a bit of handcrafted optimizations. And the results are actually pretty cool. So you have in gray, you have the performance, in this case time to first byte and largest contentful pane of the group without the preload optimization. And then you have in blue the preload optimized version. And you can actually see even from these median values that we are able to more than half the time to first byte in the median, so over all the navigations of the user. And this impacts also the largest contentful pane quite heavily in this case. This is for a page that is already not super slow, so 1.6 seconds in the largest contentful pane. Google is quite happy with that already. But it also works for pages that are even already much faster. This is, for example, a histogram of the time to first byte of a page that is already super fast. You can actually see in the distribution of load times where this preloading kicks in, because it makes kind of users that are already fast so much faster. So you have the peak of load time here at the below 100 millisecond mark, and a lot of users that kind of have an instant return on the page that they've requested. And you can also see that then in the median values on time to first byte and largest contentful pane. These are extremely good numbers, so most people don't see those when they go to PageSpeed Insights, not yet at least. But even in those cases, we can halve the time to first byte here and kind of transfer exactly that absolute impact on top of the LCP values. So works for this is not even a slow page, but works for good pages, but also works for already outstanding pages to make them even faster. Yeah, and with that, actually, the last thing is, as you've seen, this project isn't over by any means. We are just getting started to look into this much more deeper. How can we do the prediction much more sophisticated and much better? And how much performance can we actually gain if we kind of solve that whole problem? But what we can already do is gather the data, interpret that, have a system that can cope with a lot of preloads at once, and actually have data on hundreds of millions of users that where we can see that this model is working and that it's actually impacting performance really well. And if you are interested in kind of joining that journey and want to kind of build on caching technology, on a bit of machine learning, on a lot of user data, and like to impact a few 100 million users and their performance experiences, we are actually hiring as a few other companies here as well. So please reach out to me or go to speaker.com/careers, and yeah, happy to have you ask questions if you have any.